Hello everyone. So the next chapter that we are studying is alcohols, phenols and ethers. That is the second chapter of organic chemistry. Very interesting. Okay. So let us start. Firstly, we will be talking about the structures of alcohol, phenols and ethers, right? Okay. See, this is alcohol. What is alcohol? Where, in any alkyl group, like R, what is R? R is any alkyl group. O and H are bonded, right? O and H are bonded. That is the structure of alcohol, right? So it can be any, like it can also be like this is the example of CH3OH. I think you know the naming. This is methanol, right? This is the structure of alcohol, right? Okay. So now if you can see here, the angle is 108.9. Why? It is due to these lone pair of electrons. So I think you must have studied this in chemical bonding chapter class 11th, that these electrons, they repel each other. Since they repel each other, to minimize the repulsions, the lone pair repulsions, they push the bond. Hence, in alcohol, we always think that it is linear. No, it is not linear. The bond is 108.9. It is due to the lone pair of electrons, right? Okay. So you can also see the bond length. The bond length is here is 142 picometers and here the bond length is 96 picometers, right? Okay. Now the hybridization of the carbon atom is sp3 because it is making a 4 bond. Now here the reason is also given to us. See, the carbon, oxygen, hydrogen, this bond is 188.9. Basically, it should be tetrahedral because the geometry is sp3, right? It is sp3 and the shape is bent. But why it is the angle is 108.9? It is due to the repulsion between the unshared pair of electrons, right? The repulsion is causing the angle to shift like this. Okay. Structure of phenol. Phenol, there is a benzene ring. On benzene ring, we attach OH group. That is called phenol, right? You can see again, there are lone pair of electrons here. So the angle is slightly less than the tetrahedral, that is 109. Okay, the bond length is 136 picometers. And this carbon is sp2 hybridized here. Why sp2 hybridized? It is making 3 bonds are 3. So the hybridization is sp2, right? This is sp2 hybridized and there the carbon atom was sp3 hybridized, right? Okay, OH group is attached to the sp2 hybridized carbon atom. Okay. Okay, one thing we need to know that, in case of CH3OH, right, the carbon and oxygen bond length, it is bonded like this, right? CH3OH, the carbon and oxygen bond length is more, right, in methanol, but it is less in phenol. Why? It is due to the double bond character, partial double bond character because of resonance. If you would have studied, let us understand. Okay, so I'll show you the partial double bond character. What happens is, so basically if this is phenol, right? Okay, if this is phenol, okay. So what happens, there is a shifting of electrons like this. So if the electrons shift like this, which is called resonance, so the electrons shift like this, causing a double bond, a partial double bond character here. And you all know that double bond is like a strong bond. Since it pulls the electrons strongly, so this bond here becomes smaller. It becomes 136 picometers. There it was 142 picometers, right? That is the reason this is asked in the exam, right? Why the CO bond length in phenol is less than the CO bond length in methanol. Okay. Now let us move forward. This is ether. What is ether? General formula of ether is ROR. Okay. That means there are two methyl groups and in between you have an oxygen like methoxymethane. Okay. So if you want to study in detail, about the IPAC name and the structure, again, we can connect through Urban Pro. Okay. Now, see, the bond angle is slightly greater than the tetrahedral angle. Now, why the bond angle is greater? It is due to, see, now basically these lone pairs are shifting it like this, but these groups are bulky, right? Bulky groups won't like to come to each other. So they are expanding the structure like this. Hence, the bond angle, basically, the geometry is sp3, right? sp3. So sp3, the angle should be 109.5, right? But it is 111.7. Why? Because of the repulsion between the bulky groups, right? Now see, this you have to know that what is sp3, what is sp2, right? This you need to clear your knowledge of chemical bonding. Then only you will understand this, right? So we can, learn it together again by taking classes through Urban Pro. Okay. Now, let us understand, we have done the structures. Now we are going to study the properties of the alcohol. See, alcohols and phenols, they have a OH group, right? Okay, now due to this OH group is responsible for all the properties. There are alkyl groups, okay? They are responsible for some modifications. Now let us understand boiling points. Obviously, this even from haloalkanes that if there are number of carbon atoms are more, the van der Waals forces of attraction are more, hence the boiling point is also more. Also, if the number of carbon atoms increase, isn't it the mass also increases? And if the mass is more, the boiling point is more, right? So now what is this van der Waals force of attraction? You have to know it from 11th class, right? Okay. So if you can see here, obviously this will have a greater boiling point because more number of carbon atoms, more van der Waals forces, right? So more amount of boiling point, right? Okay. With branching, now what happens with branching? What happens? Let's say this is branching. With branching, surface area reduces, right? Can you see the surface area? It reduces. Basically, here the surface area is more spread out in case of a linear chain. But when I'm making a branch, I have kept the number of carbon atoms same. If I'm making a branch, the surface area reduces. This reduces the van der Waals forces, and this also reduces the boiling point, right? So boiling point decreases with the increase of branching, okay? As you increase the branches, what happens? The boiling point decreases, okay? This we need to understand. Surface area decreases, the boiling point also decreases. If you increase the surface area, the boiling point increases, right? So basically, we can say that boiling point is directly proportional to the number of carbon atoms, right? And it is inversely proportional to the branching, okay? It is inversely proportional to the branching. You can note it down. Okay. Here also there are 6 carbon atoms, but here in case because of the branches, there are low van der Waals forces causing low boiling point. Okay. So boiling point of alcohols are much higher than that of ethers or even haloalkanes of comparable masses. What is the reason? Why is this so? See, this is an alcohol, this is an ether, and this is a normal hydrocarbon, right? So boiling point of alcohols is much more greater. If you can see, the mass is same. So I told you that boiling points depends on mass. But if you can see, the mass here is comparable, but the highest boiling point is with alcohol. This is ethanol, this is methoxymethane, and this is propane, right? So why is it so? It is because of another term called hydrogen bonding. These OH groups, they make hydrogen bond with water. Water molecule is polar, right? So they make hydrogen bonding, right, with water molecule, and hydrogen bonds are like very, very strong, because of which the boiling points of ethanol are like very high. Okay. So the reason is intermolecular hydrogen bonding. Can you see? This is hydrogen bonding. Hydrogen bonding occurs only between if a electronegative element like oxygen is present, oxygen and hydrogen. It happens between nitrogen and hydrogen, fluorine and hydrogen. Okay. Okay. So this is again hydrogen bonding intermolecular between two molecules, right, in phenol. Now this is why the boiling point is very, very high in case of the alcohols, phenols, right? Now what about solubility? Now you can guess solubility will be high because hydrogen bonding, right? Polarity is more. So alcohols and phenols are soluble in water due to hydrogen bonding. Again, you can see here, right? And see, if the chain is larger, right? So the solubility decreases. Why? Because this chain is hydrophobic in nature. What is the meaning of the term hydrophobic? The meaning of the term hydrophobic is something that, does not like water, repelling water. It hates water. So basically this chain is made up of purely carbon and hydrogen, which are non-polar compounds. So solubility decreases, right? Okay, hydrophilic. This is hydrophobic part. Hydrophobic part does not mix with water. So if the chain increases, the length of the chain, solubility will come down. Okay. So this has a smaller hydrophobic part. So obviously this will be more soluble, right? High solubility for the smaller alcohol. Okay. So now there are many. So we have covered the properties, we have covered the structure. Now we are coming on to the reactions of phenol. See, there are many reactions of phenols, right? And there are many reactions of alcohols and ethers. There is preparation of all of them, right? There are many name reactions. Okay, so today what we are going to cover? We are going to cover one reaction, that is acidity of phenols. Okay. Now, what is acidity? Acidity is the ability to lose H plus ion, right? If I say phenol, if any, okay, so phenol, if you put it into, we have sodium and phenol. Any metal, if you put it into an acid, we know that hydrogen gas is liberated, right? Any metal. For example, I take HCl and I put magnesium into HCl. So hydrogen gas is liberated or released, right? So if I have phenol and if you put sodium into phenol, right? So hydrogen gas is released. Again, phenol is showing a property of an acid, right? Okay. Let us see this, what is happening here. See, what is an acid? An acid is someone who releases H plus ion. So the faster it releases H plus ion, the better acid it is. Now, what does this acidity depends upon? Let us see. Okay. Now, this is a reversible reaction. This reaction is reversible. Okay. Now, so what if this structure is not stable, this reaction will go in the backward direction, right? This is acid. So this is called the conjugate base. Okay, conjugate base. So the entire acidity depends upon the structure of the conjugate base, whether it is stable, whether it is not stable. If it is not stable, suppose here it is stable. If it is not stable, the reaction will move into the backward direction, bringing in the principle of, Lee-Chateliers principle, right? It will go in the backward direction. Okay. But now here the forward reaction is favorable. So it will go into the forward direction and release H plus ions, because as an acid, we want it to release H plus ion, right? So let us see here. So due to resonance, this structure is more stable, the conjugate base. Okay, let me show you the resonating structures. See, resonance in phenol. Okay, this is the reason of the stability of the phenoxide ion. Let us see. This is phenol and these are the resonating structures of phenol. Okay, now due to always remember, resonance brings stability. What is resonance? It is the delocalization of these pi electrons and it brings more and more stability. So if you can see here, due to resonance, there is more and more stability, right? Let us move forward. So we have a phenoxide ion. See, this is the conjugate base, phenoxide ion, right? Can you see more phenoxide ion is stable due to resonance. Hence, phenol is acidic in nature. So acidity is basically removal of H plus ion, and after removal, the leftover part, that is the conjugate base, it should be stable. If it is not stable, the reaction will go into the backward direction and we will call it as a weak acid. Let us understand. If I have alcohol, or I am comparing between normal alcohol and phenol, okay? So if you would see the alkoxide ion and if you would see phenoxide ion, which one is more stable? Obviously, phenoxide ion is more stable because, it. So I will tell you one simple thing. If the negative charge here is more, isn't it the positive H plus would come back, right? But what does the phenoxide ion do? It delocalizes the negative charge, right? So negative charge reduces, hence H plus will not like to come back. But in case of alkoxide ion here, right, we all know that alkyl groups, they show inductive effect. What is the inductive effect? They increase the electron density on this oxygen. Already there is a negative charge. If we increase the electron density, what will happen? The H plus ion would definitely want to come back and, the acid, it will again form like alcohol, right? So it will be a weak acid, right? Okay. So basically the conclusion here is phenol is a stronger acid than alcohol. Phenoxide ion is more stable, right? This is more favorable, fast reaction. Okay. So it is more acidic, right? Phenol is more acidic, but here this reaction is slow. H plus is released in low concentration and this is less acidic. Why? Because this RO minus, that is the alkoxide ion, is not stable, right? Why? Because of the inductive effect of the alkyl group. Okay. Now, there are also the substituents which affects the rate of acidity. Okay. See, we want to reduce the negative charge. If I would go back, isn't it? I want to reduce the negative charge on the conjugate base so that this H plus does not come back. Now, how do I reduce the negative charge? By adding electron withdrawing groups like NO2. So these electron withdrawing groups, they decrease the electron density. So if they decrease the electron density, basically the negative charge would become less and the H plus ion would not want to come back. Also, by decreasing the negative charge, the conjugate base will become now more and more stable, right? So we want the conjugate base to become stable. So we have electron withdrawing groups, we have electron donating groups. Now electron withdrawing groups show minus I effect. As I told you, electron donating groups, they show plus I, means they increase the electron density on the oxygen. Here, these groups, they decrease the electron density. Let us see. Okay, so basically these groups like halogens or NO2, they increase the acidity, but decreases with distance. That is, if NO2 is attached at a very, distant places, then it will not decrease, then it will not increase the acidity that much. Okay. Let us understand. So if you can see this, para-nitrophenol, ortho-nitrophenol, meta-nitrophenol, right? Now, this effect is more pronounced at ortho and para position. Why? Because if you see at the resonating structures, the negative charge was present at the ortho and para position more. The negative charge was not at the meta. See, Why do we want to reduce negative charge? If we reduce negative charge, the conjugate base will be more stable. More stable means more acidic. Also, if we reduce the negative charge, the H plus would not want to come. That is what we want, right? A good acid is something that releases H plus ion very fast. For that, the conjugate base should be stable. So make it stable, we need to add these nitro groups, which are what? Electron donating group. Sorry, electron withdrawing group. They decrease the acidity, right? And the effect is more pronounced at para. So obviously ortho and then meta. But why is ortho again less? Because still there is some steric hindrance here. Can you see the molecules are close together? So there is kind of a steric hindrance crowding. Okay. So what decreases the acidic nature? That is, if something increases the electron density, like, like this is cresol. What is cresol? If a methyl group and phenol group both are attached, we call it cresol. That is, so here you have a CH3 and a OH group. CH3 group increases electron density. This also increases and this also increases the electron density, right? Okay, but it will not work at meta position because, at meta position, the electron density is, again, the structure has very less electron density, right? Okay, so if you can see inductive effect, here they will show inductive effect, right? Let us see. So this is near to OH group, right? Okay. So if you would see, this is the decreasing the acidic nature of phenol because of the presence of the CH3 group, right? Okay. Let us understand. So with the help of this concept, we need to understand now which is more acidic. This is more acidic. Why? Because this CH3 will not increase the electron density that much because here there was anyway less electron density. There was no charge, but the negative charge was here and it was here, right? Here there was negative charge. Now here if we have the negative charge and CH3 is putting more electrons, right? Already there was negative charge at that para position and CH3 is adding more electron density. What will happen? Right? It will disrupt the acidity. It will make it less. It will, decrease the stability of our structure. Again here, now this is closer to the OH group, right? So there is already negative charge. In the resonating structure, we have seen negative charge is at 3 places, that is ortho and para. So this CH3 group, it increases the electron density at the ortho and at the para positions, right? So if the electron density is increased at the ortho and para positions, the acidity becomes less because the stability decreases. Now here the stability decreases again, right? Let us move forward. This is quickly a test that you can do yourself. I have arranged the elements, right? You need to compare the acidic nature, arrange them in the increasing or decreasing order anyway. We have para-nitrophenol, metacresol, ortho-nitrophenol, orthocresol, meta-nitrophenol, phenol, and paracresol. Okay, so just arrange them and take 2 minutes, pause the video. In the next slide, I'm showing the answer. So this is the answer, right? So you can compare your answer and check it, right? So I really hope you understood about acidity. You understood the basic structure of, alcohol, phenols, and ethers, about their properties like solubility and boiling point. So if you want to learn more in detail, as this was just a short video of the chapter, if you want to learn more in detail, if you want to practice board questions, you can get in touch with me. We can work together, right? Okay.